We're in chapter 4 before the holiday there. So in chapter 4, we talked about something, I think. What that was, I don't remember. But science, perhaps chemistry-like stuff. I don't know. Maybe. All right. So chapter 4, let me see if I can jog my memory. I think we talked a little bit about symbols for chemicals or elements. Yep. So symbols for elements, remember that they're either one letter like potassiums, or they are two letters as we talked about, which like lead, which is Pb. Remember that if it is a two-letter symbol, the first one's capitalized, the second letter is not. And then really we talked about the atom for a good little chunk there. And we talked about really some experiments that helped us understand the structure of the atom. We talked about Dalton's atomic theory and the different parts of it, the parts that are still correct, some parts that are not so correct, like again, that all atoms of the same element are identical to each other is not correct anymore. But things like basically atoms enter into chemical combination by breaking and making bonds, that is all still good. Remember that a lot of the early sort of work was done with CRT tubes or cathode ray tubes done by Thomson, along with, I think we talked about the oil drop experiment a little bit, which was Milligan. And remember that sort of both of those helped us understand a little bit more about the electron, which is negatively charged, and they're able to get the mass of an electron, which was something like 9.09 times 10 to the minus 28 grams, give or take a little bit there. And remember that this really led into sort of the idea of that the atom was neutral. So sort of the discovery of electrons sort of moved us that we have these negatively charged particles, but there must be something that's sort of positively charged. And sort of the earliest sort of model was the plum pudding model put forth by Thomson, where the atom was thought to be a sphere of positive charge. And we had our electrons that were sort of embedded inside the sphere. And they felt that in that early model of the atom, that most of the mass of the atom was made up of the electrons. And this was sort of like an accepted model until really the next sort of big discovery in the process of understanding the atom came about. And that was Rutherford and the gold foil experiment. And what Rutherford did was he shot those alpha particles, which are positively charged radioactive particles, at pieces of gold foil and other metals. And again, as we talked about, what they sort of thought would happen because of this model of the atom was mainly positive sort of charge spread out, that the alpha particles would sort of go through, but there would be some deflection as it went through, sort of positive with positive, but heavy and moving fast. We'll be able to sort of puncture through. They were actually really surprised when they did the experiment that they saw that most of the alpha particles went right through undeflected. But they were able to see at certain points along the way, those alpha particles were really scattered at fairly large angles. And as we talked about, what that meant was it had to hit something really, really densely positive. And so essentially what happened was they had to sort of throw out this sort of early version of the atom and come up with sort of a new model of the atom. And that was that the atom is mostly empty space. And again, that's why most of the particles had no problem. They just kind of sailed right through. It did contain a dense positive core, which is known as the nucleus. Remember that sort of later studies found that the protons, which are positively charged, are found in the nucleus, along with the neutrons, which have no charge, are found in the nucleus. And they said that the electrons are out in the empty space. moving around in a pretty random motion. There is some attraction between the electrons and the nucleus, as one's negative, one's positive, so kind of holds the electrons there. And one of the major differences between the two models and the current model here is most of the mass of the atom is the nucleus. And that does make sense based on the idea of something else that we talked about, was out of the three subatomic particles, the protons, which are positively charged, the neutrons, which have no charge, and the electrons, which have a negative charge. Both the proton and the neutrons about 1,800 or so times heavier than any electron, with actually the neutron being the heaviest of all three particles, just barely edging out the just barely edging out the proton. So the neutron is the heaviest, followed very closely by the proton. And then the electron is really the lightest of those three, again, about 1,800 or so times lighter than a proton and so forth. So this is really sort of the accepted version of the atom that came out of these sort of experiments. We then got into some of the other aspects of an atom. We talked about atomic number, I believe, and isotopes. So the atomic number is the number of protons there are in an atom. And that atomic number can be found on the periodic table. And it is the number up on top of the symbol. And as we talked about, the atomic number is really important because it is the number of protons there are. And as we talked about, there is no number that basically repeats. So every element has its own atomic number, which means every element has its own number of protons. And the importance of that is you basically know what element you're talking about if you simply know how many protons it has or what the atomic number is. So you'll always know what element it is based on the number of protons. We also talked about the mass number, which is the number of protons plus the number of neutrons. Remember, as we talked about, the mass number is not found on the periodic table. So again, that number on the bottom is not the mass number. That is actually the atomic mass, which we'll talk about today. But it's not the mass number. It's important, those two numbers, that if you take the mass number and you subtract the atomic number from it, that will tell you the number of neutrons that an atom has. And when we calculate how many protons, electrons, and neutrons there are, and you calculate the mass number and the atomic number, they all should be positive whole numbers. So that also should tell you, if you have the urge to go to the periodic table and try to use that number on the bottom as the mass number, pretty much none of them are whole numbers. They're all decimal numbers, so you definitely should not be using those. Lastly, I think we talked about the idea of writing these symbols. So remember that we use the symbol. Top left of the symbol is where we write the mass number. Bottom left is where we write our atomic number. And we did also see that sometimes it is written, say, something like this, the symbol plus a number. And when it is like that, that is the mass number, the way it's written. In relationship to this, we talked about things that actually gain charges, which are ions. And there are two types of ions. And again, ions are things that have charges. There is a cation, which becomes positively charged as a result of losing electrons. And typically metals are those guys that will kind of do that. There's also anions, which are negatively charged ions, and they are negatively charged because, frankly, they have gained electrons. So they have more negative charges than positive charges of protons, so they're overall negative. And those are typically our nonmetals that do that. So when we're calculating something like how many protons, electrons, and neutrons there are, if something does have a charge, really the only thing that changes is the number of electrons. And if it has a positive charge, it means it has lost a number of electrons from the neutral guy. If it has a negative charge, it has gained that many electrons. How many it lost and gained is actually equal to the charge. So something has a +2 charge, it means that that substance or ion has lost 2 electrons from the neutral guy. and if something had a -3 charge, that would mean that the minus has gained electrons and it gained 3 electrons from the neutral guy. Whew. Any questions on any of that stuff there? Yeah. All right. So I believe that's where we left off. All right. All right, so isotopes was another thing that we talked about. And just to wrap up on isotopes, remember that isotopes are the same element, but they do have different masses. And the reason they have different masses, as we talked about, is because they have different numbers of neutrons. They obviously will have the same number of protons, otherwise they would not be the same element, but they do have different numbers of neutrons. One of the nice things about normal sort of chemical reactions that take place, pretty much is all electrons are involved in that. So really chemical reactions are nothing more than just the electrons and bonds being broken and made. Nothing in the nucleus, no protons or neutrons ever really get involved in traditional chemical reactions. So the one nice thing about isotopes is a lot of them are radioactive, for example. So a lot of people, when they do research, they will use maybe a radioactive version of an element if they're interested in, what's happening with that. For example, I used to do research where we use copper-64, and it basically does the same chemistry as non-radioactive copper, say in your body or in a sort of a mechanism. And just by following the radioactivity, you can figure out, where the copper ends up, where it doesn't end up, just by sort of using something that has radioactivity. Isotopes are also used in medicine, radioactive ones as well for imaging. They're also used for treatment. Sometimes they used to implant radioactive isotopes into tumors and stuff like that to sort of shrink them and stuff. So there's a nice advantage of isotopes. But again, it's really just the number of neutrons that change. So let's talk a little bit about chemical composition. Speaking of that number that's on the bottom of the periodic table, that is where we're going. So looking at that number on the bottom, that is the atomic mass of an element. And again, that is different than the mass number that we were just talking about. So one of the fundamental properties really of all atoms is basically the mass of it. It is really based on how many protons, electrons, and neutrons that it has. Obviously, atoms are extremely small, so you can't just pick one up and put it on a scale or a balance and weigh it. So a lot of times in chemistry and in science, when it's really hard to sort of measure one thing kind of directly, they oftentimes will kind of make something a standard and then kind of compare everybody else to that. So for the atomic mass, they actually used an isotope of carbon as the standard, and they used the carbon-12 isotope as basically the standard isotope to compare the atomic masses of all the other elements. Carbon-12 has a mass of exactly what is known as 12 atomic mass units. And that is sometimes AMU. So, for example, they looked at hydrogen and said it's only about 8.4% as big as the carbon-12 isotope. So they basically did a little math sort of calculation. That's like 8.4% converted into a decimal. Move it 2 places to the left or divide. They multiplied it by 12 and they get sort of the number that we see there on the periodic table. So you can go to the periodic table, and for any of the elements that are listed there, you can go and grab that number off of it. Typically speaking, when we do grab that number for atomic mass, and really later when we talk about molar mass, the traditional amount of numbers that you take is usually 4 significant figures. So depending on your periodic table, there may be a lot of numbers underneath there. There may not be a lot of numbers, but the normal process of how many you should use off the periodic table is 4 significant figures. And if you pull that off the periodic table, basically what that represents is that there is 1.008 AMU, atomic mass units, in an atom of hydrogen is basically what that sort of relationship is. And you can do that for anybody else on the periodic table. If you look under oxygen, you might see 15.99999, but basically it's like 16. And again, what that means is the atomic mass of oxygen is 16 AMU per atom. Outside of this chapter, to not use the units of AMU very much. We will use a more useful unit, and we'll talk about in a later chapter, which is known as molar mass, which are units of grams per mole, basically. So we can, as we will see in a later chapter, basically go and take those numbers off the periodic table the exact same way, except that they would represent how many grams there are in 1 mole. And obviously, we'll talk about what moles are in a little later chapter. They're numerically equal to each other, the atomic mass and molar mass, as long as the units are changed. Now, you can find obviously all the atomic masses that are listed there. And once again, they are the one that's on the bottom. If you needed something more than just the element by itself, you could just add up all the parts if it was some type of molecule or something like that, if you needed the atomic mass of it. Now, if we do look at carbon, though, what we actually see underneath it is actually this number, 12.01. And you may say to yourself, well, if carbon is sort of the standard that they use for atomic mass, and it has a mass of exactly 12, why does it say 12.01? So what we are actually seeing when we look at the periodic table and all the numbers that are on the bottom, the atomic masses, they're actually average atomic masses. So what the numbers that we actually see there, although most people don't ever say average atomic mass, they just say atomic mass, are the average atomic masses of all the naturally occurring isotopes for that particular element. So there can be 1 or 2 naturally occurring isotopes, 3 or so isotopes that naturally occur for a particular element. And they do a calculation using the masses of all the different isotopes that naturally occur for that element. And that is really how we get the number that we see on the periodic table. So if you wanted to do that calculation, the way that you do it is the atomic mass, you would take the percentage of the first isotope of that element. You then would times it by the atomic mass of the first isotope. You then would actually add it, not multiply it, which is like what everybody always wants to do at this point, is like multiply it, but you actually would add it to the percentage of the second isotope times the atomic mass of the second isotope. And if you had a third isotope, you would just continue that pattern. You would take the percentage of the third isotope times the atomic mass of the third one. And again, if there was 4, you just kind of continue that pattern. When we talk about the percentage, what we're talking about is sometimes referred to as the percent abundance, or the relative percent abundance. Is basically a percentage of like, hey, there's 40% of this isotope that naturally occurs. There's 60% of this isotope that naturally occurs. 60 and 40 is 100%. So that's all the naturally occurring isotopes for that particular element. Or maybe it's like, 25 for this isotope, 25 for this one, and 50 for this isotope. So somewhere in these type of problems, they'll usually give you something that says something like that: the relative abundance, the percent abundance of these isotopes, and the percentage at which they naturally occur. So for example, if we do look at like carbon, which is this one here, this is the carbon 12 isotope, which is naturally occurring, and this is the carbon 13 isotope. And these are the masses of each of those isotopes. So the carbon 12 isotope has a mass of 12. The one there has 13. These are the percentages that they occur. So basically, the carbon 12 isotope occurs about 99% of the time, and the carbon 13 isotope occurs about 1% of the time. When you do a problem like this, or given information like this as a problem, you do want to make sure that these percentages sort of add up to about 100%. If they don't add up to 100%, that means you are missing an isotope somewhere, right? So it should add up to 100%. if you have all the naturally occurring isotopes. And again, if it doesn't by some chance, you might be missing something. So to calculate this, you can do one of two things. Basically the calculation there is at the bottom, but basically if you're going to calculate the atomic mass, you would take your first isotope, which is our carbon-12 isotope in this case, and you could either move the decimal place 2 places to the left to convert our percentage into a decimal, or you could divide by 100, and that would do it for you. You could times it by the atomic mass of that first isotope. You then again would add it at this point to our second isotope, which is the carbon-13 isotope. And again, at this point, you can do one of two things. You could take the 1.11%, divide it by 100%, and it will move the decimal place for you if you like to do it that way. And you're going to times it by the atomic mass there of our carbon-13. And as you can see down there, 12.01 AMU, although I feel like I get 12.02 when I do it on my calculator, but we'll go with 12.01 here. And that is the number that we do see when we do look at carbon on the periodic table, which is 12.01. Question on that there. So if you need to calculate the atomic mass, that is how you would do it. Basically percentage times the atomic mass of each individual isotope, basically added together. Any questions on that one there? All right, so I think there's one for you to try. Let's see. There is. All right, so bromine has 2 stable isotopes, bromine 79, that occurs about 50.70% of the time, and bromine 81, it occurs about 49.32% of the time. The atomic masses of each of those isotopes is 78 and 80.92. What is the atomic mass? So take a moment and calculate it, see what you come up with. If we just kind of gather up the information for each, we have bromine 79, and that occurs about 50.70% of the time, and it has a mass of 78.92 AMU. We also have bromine 81, and that occurs about 49.32% of the time, and it has a mass of 80.92 AMU. Again, I would want to maybe take a look at both of these percentages and make sure it's about 100. It probably won't be exactly 100, but it is. So we're good to go. We're not missing any isotopes. So to calculate the atomic mass here, we're going to, again, we need to convert our percentages into decimals. So you can move the decimal place 2 places to the left or divide it by 100. To do that, that gives you 0.507 times 78.92 AMU. That's basically our bromine 79 isotope. We're then going to add this to same deal. We need to convert that into a decimal. So if you wanted to include it in your calculation, that is essentially what you are doing, dividing by 100. You then would times that by the atomic mass of that isotope, which is 80.92 AMU. And once again, that would be basically our bromine 81. And I think if you do that, that's a 79.92, I think, yes. Which looks like it would be D. Any questions on that? No? Good? Yep. So it is important to remember that although we do basically use these as atomic masses, they are the average atomic masses of the naturally occurring isotopes. You would never, for example, in this particular case, find a bromine that has a mass of 79.92. You would either find the bromine 79 isotope that has a mass of 78, or you would find the one that's bromine 81 that would have a mass of 80.92. Same thing with the carbon. You'll never find one that's 12.01. You'll either find one that's the carbon-12 isotope, which is a mass of 12, or the carbon-13 isotope that's a mass of 13. But we do use this as the sort of atomic masses as a sort of an average of all those naturally occurring isotopes. Any questions on that there? All right, then let's talk about the periodic table. That's a periodic table. Good talk. All right, so we'll continue on. Now, a periodic table gives a good amount of information about the elements, some of which we've talked about. But first off, a column on the periodic table is what is referred to as a group. If you're really old like me, a family, but really nobody uses families all that much anymore. Now, when you look at a periodic table, depending on what periodic table you look at, like that one hanging there, one in your book, one up here, there's oftentimes a lot of different numbering that you see on top. There's sometimes what is referred to as the A numbering. There's sometimes the B numbering. And like up there, it's just like 1 through 18 type numbering straight across there. When we look at groups, we use what is referred to as the A numbering in most chemistry classes, is what is sometimes also referred to as the representative numbering. This is group 1 right here. It actually starts with lithium. So even though hydrogen's hanging out over there, and that is the element right here, that is hydrogen. Even though hydrogen is hanging out there, it's actually not part of group 1. We'll talk why that is in just a second, but group 1 actually starts with lithium. Right next door is group 2. We then skip all this middle part in terms of numbering, and we pick back up here at group 3, group 4, group 5, group 6, group 7, and group 8. So that is the proper way that we number groups. And again, groups basically are going down, up and down there on the periodic table. We go left to right on the periodic table across a row. That is what is referred to as a period. And that is going that way on the periodic table. And there's actually 7 periods, and it is numbered here. So that is 1, 2, 3, 4, 5, 6, and 7. So there are 7 periods on the periodic table heading in this direction. And we deal with 8 groups on the periodic table. As we've been talking about, the number again up on top there of the symbol is the atomic number. And as we talked about last time and today as well, that obviously is the number of protons that there are in an atom. Now, when we look at the periodic table, it's really broken up into 3 different categories. There are metals, there are nonmetals, and there are what are referred to as metalloids. On most periodic tables, right around boron, you usually will see like a staircase sort of etched in there on most of the periodic tables that you find. And really kind of to the left of that staircase, and not pictured here, but the 2 rows that are typically on the bottom of the periodic table, those are metals, and metals are good conductors of heat and electricity. They're also malleable. You could hammer them into sheets, you could pull them into wires. They typically have a shiny appearance. Pretty much all metals are solids at room temperature, except for mercury, which is number 80. And mercury is a liquid. So on a lot of periodic tables, mercury sometimes is a different color, how it's written, but pretty much all other metals will be a solid at room temperature. To the upper right are our nonmetals of that staircase. So to the upper right here of the staircase are nonmetals. Nonmetals are pretty much the opposite of metals in terms of their characteristics. They are poor conductors of heat and electricity. They're dull, they're brittle, they're insulators. They also have a much more varied sort of states. Some nonmetals are gases. A lot of those diatomic molecules that are elements that we talked about, like hydrogen, nitrogen, oxygen, chlorine, fluorine, these are all gases and also the elements. Bromine, which is also diatomic, is a liquid, and things like carbon and sulfur are solids. Now, coming back over here to group 1, and this is hydrogen. Hydrogen is what type of element? It is a nonmetal. Yeah, so hydrogen is actually a non-metal, even though it's hanging out with all the metals. And that is why hydrogen is really not part of group 1, because it's actually a non-metal. It's over there because it has some interesting characteristics, one of which we talked about. It has 1 proton and 1 electron and no neutrons, but it does in a lot of cases behave very similar to some metals. So you'll find hydrogen usually over there, but it is a non-metal and not part of group 1. On older periodic tables, they used to also lay up hydrogen oxygen on both sides, and you would actually find it over there on the right-hand side as well. The staircase part are our metals, our semi-metals. I'm sorry, our metalloids are semi-metals. Some books, I can't remember if yours does or not, will include boron as part of the metalloids or semi-metals. So if you kind of think about where they are located, basically to the left of them are metals, to the right of them are non-metals. So they're kind of in between the two. And what semi-metals have or metalloids have are characteristics that are very similar to metals. And the same element will have some characteristics that are very similar to non-metals, why they're semiconductors. So they have the ability to kind of have properties that fall to the right and left of them, which is why they're placed there. The same element will have those different ones, some of which are metals and some of which are non-metals sort of properties. Now, when we talk about the groups, there are certain names for particular groups. So starting with group 1, which is here, and once again, starting with lithium, those are what are referred to as the alkali metals. Hanging over there to group 2, those are what are referred to as the alkaline earth metals. The word alkaline means basic. And a lot of strong bases actually come from group 1 and group 2 on the periodic table. Things like sodium hydroxide, potassium hydroxide, calcium hydroxide pretty much hook up hydroxide, which is OH, with any of those guys, and you get like a strong base. So that's why they're sort of referred to that. Hanging over here to group 7, these are our halogens. And those also are a lot of those guys that come as diatomics like F2, Cl2, Br2, and I2. Right next door, and we'll see it on the next slide, right next door is group 8, and that is also known as the noble gases. Your helium, your neon, your argon, your krypton, all your ons there are noble gases. They are monoatomic, which means they typically come as ones. Noble gases also mean that they are sort of a class set aside. They are chemically inert, which means they do not react with things. They will react with themselves, but it will not react with others. So they're pretty stable and don't really react all that much with things. And as we will talk about when we get to bonding, it is pretty much what everybody tries to achieve. So the whole idea behind bonding, as we'll talk about, is for everybody basically to become like the noble gases, really nice and stable sort of situation in terms of their electrons. A couple other things here between group number 2 and group number 3 in this region here. These are our transition metals. So basically this box here in blue. So those are our transition metals. And one of the things we'll learn about transition metals are they, for the most part, make multiple types of charges. So something like copper in some cases can make a +1 charge, in other cases can make a +2 charge. There are some that have fixed charges, but most of them will have some variations. The last 2 rows down here, these are what are referred to as the lanthanide series and actinide series. They're usually put on the bottom, otherwise your periodic table is super wide, like you need a wall to do that. Only one classroom I teach at actually has that done, and it like takes up the whole wall. And that's because if you look at the atomic numbers, that is 57, that is 72, 58's actually right here. And that is 89, and that's 104. 90 is right here. These two rows technically go right there. So that is technically where those two rows should go. And that's why they are also sometimes referred to, in addition to lanthanide and actinide, which are the two elements they follow, they are also sometimes referred to as inner transition metals. Because technically speaking, they should go right about there on the periodic table. Any questions on the periodic table? You need to know groups, which way they go, the numbering of the groups, the 1, 2, 3, 4, 5, 6, 7, 8. You need to know periods, which way they go. You need to know what things are metals, which ones are non-metals, and which ones are metalloids. You need to know the names of the special groups where the alkali metals are, alkaline earth metals, the halogens, and the noble gases are located. Obviously, as well, where the transition metals are located. Any questions on that there? What's that? Yeah, you need to know that, yeah. The exam would be good, yes. In general speaking as well, for the it as well, but for the exam, you do need to know those things, yeah. Any questions on periodic table? We talked about, I think we're going to talk about symbols that you should get an idea of names and stuff like that go with the symbols. A reminder that the periodic tables that you will be given will not have names. They will have symbols, but you do need to kind of know names. All right, so what we're going to talk about for the rest here of this chapter is really about electrons and sort of where electrons are in the atom, and as they sort of transition from one energy level to the next, what is sort of happening. First off, there was sometimes spectrum, and basically energy is given off in the form of waves, and waves basically here look something like this. And they have what is referred to as a wavelength, which is abbreviated with lambda there, wavelength. They also have a amplitude, which is basically the height of it. And they also have what is referred to as a frequency, sometimes abbreviated with the nu symbol, although people call it a V. It's not really a V, but it's the nu symbol there. And specifically for our purposes here, when we have electrons that are, for example, on different energy levels, say we have an electron on this energy level, which is lower than, say, this energy level here. When an electron, or in general, an atom gains energy, when it gains energy, the atom, this electron will then absorb energy, and it will be able to really go up in terms of its energy level and find itself at a higher energy level. Electrons are much like us. We usually like to be in the lowest state of energy, and so do electrons. And lowest state of energy in chemistry are really the most stable sort of situation. Things that are in high states of energy are not really stable because they do want to get kind of back to that lowest state. Now, in order for that electron to really kind of come back down in energy, it has to give off that energy. And it gives off that energy really in a form of a wave that has a specific wavelength. And this idea is really when we talk about the law of conservation of energy. So we don't create energy or destroy energy, but it is transferred. So if somebody gains a certain amount of energy, it's got to lose a certain amount of energy when it comes back down. If this wave that comes off finds itself, say, in the visible part of the spectrum, and that visible part of the electromagnetic spectrum is where we see colors, like our Roy G. Biv, I think they call it these days. Red, orange, yellow, green, blue, indigo, and violet. We will see colors. It's basically how fireworks work, right? They shoot off the fireworks. There's an explosion with a lot of energy. all the elements that are sitting there, their electrons go really high in energy levels. As they come back down, which happens very quickly, we go, ooh, blue, red, pretty colors that we see. So because we could see those colors because they're in the visible part of the spectrum. Now, when sometimes electrons transfer, they may not be in the visible part of the spectrum. They may be in like the infrared part of the spectrum, and we may feel heat that's coming off, right, as a result of those electrons transitioning. So depending on the wavelength, there is the electromagnetic spectrum, which is really how energy moves through space, and they move through space through these waves. And there's really a relationship between the wave length and its energy. So something like that that has sort of a longer wavelength will have a lower frequency, which means a frequency is how fast it occurs per second, or how many waves basically pass a point per second. And it usually will have a lower energy, as opposed to a wave that has a much smaller wavelength. A much smaller wavelength means that we have a higher frequency. And that little new, there's a frequency, and it also means we have higher energy. So as electrons sort of transition from one energy level to the next, they are releasing sort of energy in the terms of waves. And depending on sort of the wavelength, it may fall in different parts of what's known as electromagnetic spectrum. On the left-hand side, this is a longer wavelength. Which means on this side, it is lower in energy. On this side, it's a much smaller wavelength, which means it is higher in energy. So if we look on the left-hand side here, we have radio waves, which, you know, we listen to the radio, not going to kill us too much, right? So not so much energy. By the way, when you dial your radio in, I know that there's no dials anymore. I know you push buttons, or maybe I have a dial too. Don't feel bad. I got those there. But when you dial it into a radio station like 95.5, that is 95.5 megahertz. That is the frequency of that radio station that you're dialing into. Next, in terms of, we got some television and stuff. And we have some microwaves, right? So microwaves have a little bit more energy, as a smaller wavelength than radio waves. That's good because when we put our pizza in the microwave, right, it has enough energy to spin our water molecules really fast, and we get pizza in like 3 minutes, which is good for science, right? That's right I'm talking about. If we go next, we have infrared, which has a smaller wavelength, even more energy. That is the part of the spectrum, if it comes off there in terms of its wavelength, where we feel heat and energy. Next, we have the visible part of the spectrum, which even with the colors have different energies. This is red on this side. This is violet over here, and Roy and G in the middle there, the orange, yellow, and all that. And on this side, that's 700 nanometers versus 400 nanometer. The purple side has these shorter wavelengths, which means it is higher or lower in energy than the red side. It is higher in energy, yeah? As the red side has lower wavelength and lower in energy. So even the colors, depending on what colors you see, have a different sort of amount of energy. Past visible part of the spectrum is the UV or ultraviolet part of the spectrum. That is why we sunblock up, right? So we don't get too burnt or anything like that, because it's a lot of energy there. Next is X-rays, which is why they throw a lead vest on you and leave the room when they shoot the X-rays usually, right? Because it's pretty high in energy. And the last part of the spectrum, which is the shortest wavelength, are gamma rays. Gamma rays are basically radioactive rays. They're just pure energy. They're very, very high in energy. And if you work with them, you take a lot of precautions to make sure you do not injure yourself or anything like that. So the electromagnetic spectrum, in relation to what we're going to talk about here in this chapter, is really about the electrons as they're transitioning. And again, they're going to give off energy. And again, depending on where that wavelength is as to where it may fall. When an electron goes from a lower energy level to a higher energy level, the atom needs to gain energy to do that, absorb energy. When the electron goes from a higher energy level down to a lower energy level, the atom needs to lose energy to do that. It's got to allow the electron to come back down. So when electrons transfer from lower to higher, everybody's gaining energy to do that. And when they go from higher to lower transition, the atom is releasing that energy again in the form of a wave, which will correspond somewhere here. Any questions on that there? All right, we were laid up there for